Some basic stuff that we got to talk about. Two types of switches. We got a ground side switch and a positive side switch. One's called a pull up, so this supplies current. When I close the switch, this line goes positive. When I open the switch, this line goes to 0. Now, there is inside a PCM, it's real common, they need to have what's called a dropping resistor across it. Because if you don't have the dropping resistor there, when I open the switch, we're going to get all kinds of stray transient voltage on this line. So this dropping resistor will make sure that this line goes to actually 0 volts. Okay. The other type of switch is a current sink, or a sink switch, or a pull down switch. And what this does is, on the other side of this dropping resistor, as we call it, we have some type of nominal voltage, usually 5 volts. It's pretty common. When we close the switch, that pulls this point right here down to 0 volts. When we open the switch, it jumps up to whatever our reference voltage is, in this case 5 volts. So those are the two main types of computer switching, or any type of switching, that we use in the automotive environment: pull up and pull down. Okay, and then we have electrical measuring. Voltage is measured in parallel to the load across it. Source voltage needs to be supplied. Don't screw that up, or else you'll blow up the meter. Resistance, measured in parallel to the load, but can't have any voltage applied to it. Needs to be disconnected from the circuit. Whatever you're measuring, you should, as a matter of good diligence, is whatever component you want to measure resistance of, remove it from the circuit, disconnect it from the circuit, is generally what I would suggest. Current is usually measured in series, unless you have an amp clamp, and we'll use those. And it's usually measured any place in the circuit, either before or after the load. And it needs to be on in order to measure current. We good? Basics. All right. Now, we can use a digital voltmeter to measure current. My preferred method, me personally, is using an amp clamp. We have them. Digital voltmeters are generally not safe for high current loads. Generally, anything over 7-8 amps is kind of questionable using a DVOM for. They're fused at 10, but that fuse is rather expensive, and I would prefer not to blow one. They are very accurate when dealing with low current applications. So if I'm dealing with something with very, very low current, that is a good way to do it. Amp clamp is safe for high current draws, although unless you have a very specific setup with a specific, very expensive low current clamp that isn't any good for high current, those work generally pretty well for low current. But average, less expensive current clamp doesn't work well below into the milliamp stage. Relays. Think of relays as an electronically operated remote switch is the easiest way to think of it. Usually it's used for high current draw switching. Switching out of a PCM or switching out of a switch is generally not rated for high current. High current switches are expensive and they tend to fail after a while. So we use relays to do this. Now there's two sides to keep in mind: load and control. And these relays come in many different shapes and sizes, although there are on many vehicles, I'll pick on, virtually most of them made, with the exception of, Toyota and a couple of the Asian manufacturers. They use what's called an ISO standard relay, which the pins are in a ISO standard configuration, and there are numbers associated with these. 30, 87, and 87A are this side of my relay. This is the load side, and then 85 and 86 is always going to be my control side. So here's my coil, this is my control side, and then here's my heavy duty contacts, which are my load side. Okay, and if you see these numbers, they usually correspond to the same layout. So if you can remember this layout, or write it down, stick it in your toolbox on a Post-it note, this can really help you identify the pins on a relay anyways. And then there's a bunch of different types of relays. By far the most common is this SPDT. This is single pole double throw. This one is the most common. So this is the coil. So when this relay becomes energized, it has a normally closed contact with C and B, and then it switches over to A when the control is energized. We okay? But we do have to watch it. We do have some other weird relays that look the same and they're not internally. So you see guys, swapping relays around in a fuse panel. I would be very careful to make certain that that is the correct relay. Okay? Just because it looks the same, just because it plugs in is not necessarily you're not necessarily assured that that is the proper relay for that position. Got it? All right. So what's inside a relay? Well, it's pretty simple. We have this, low amperage coil. Typically these things draw 1/3 to 1/2 to 3/4 of an amp, depending on the relay. This coil right here, it would be the load on the control side of the circuit. And then we have, just the load side of the circuit. The control side of the circuit is what carries the heavy amperage that does all the work for the relay. So this coil is typically connected to a computer control or some type of a small switch. Think of like a horn switch or something along those lines. A lot of these relays, well, all relays, when the coil gets energized, it builds up a magnetic field. And then when we turn it off, that magnetic field collapses, and we can get hundreds of volts spiked back through the control side. And if that's a computer-driven circuit, that can harm the computer. So what they generally do is quite a lot of manufacturers use what's called a resistor. And it's just kind of like that dropping resistor, but any huge voltage spike is going to be taken up by this very low amperage resistor. Get it? Or they'll use a diode. So the directionability, the direction that the current flows through this control side of the circuit is kind of critical on these diode spike limiting relays. Got it? Do need to be careful with this. All right. Diagnosing the relay. Now, the easiest way to remember it is you have two separate sides to the relay. There's the load side, does the heavy amperage, and then there's the control side, generally controlled by a computer. We okay with this? So if we are diagnosing a relay, you have to diagnose two different sides. Now, remember, the relay on the load side is the switch that turns on an external load. However, the control side of the relay, that coil, that is the load on that side of the circuit. And that seems to be where people get caught up in trying to diagnose a relay. There's two different sides. One side is a switch, and the other side is actually a load in the other circuit, controlled by an external switch. Does that make sense? Both of them need to be checked when you're checking a relay. You can't just check one side. Although what you can do is, once you identify the pins on the relay, you can jump the load side of the relay. You can jump across that switch and activate the load to see if that side is working. The other thing you can do is literally put your finger on top of the relay and feel if it clicks. Because if it clicks, that tells you that the control side is working. Get it? So I can jump it, the relay plug, take the relay out, jump across the plug, turn on the load. We're going to be doing that in the lab. And then check the control side. You get it? And that can be checked with something as simple as a test light across it. Relays operate on 12 volts, and generally they're about 1/2 amp. So a small little light bulb pinned into the control side, turn it on, turn it off. Light should come on and off, telling you that the control side is working. Get it? So usually, if there's a relay in the circuit and it's simple to get to, that is usually my go-to point when I'm checking a circuit, because everything on the relay circuit comes together at the relay and then goes off from there on the load side and the control side. But I can get to both sides of the relay. Got Got it? That's my tip.